Okay, welcome to Phototech lecture number 27. Today we're happy to have Ken Turkowski, who's been a Googler now for about 5 months. Before that he worked at various places like Adobe and Coma, and for a long time at Apple, where he implemented QuickTime VR and a bunch of stuff like that. And coincidentally, Ken is probably the person at Google that I've known the longest. I don't know if he remembers, but we met when I went and gave a lecture at Dave Patterson's RISC machine class at Berkeley around 1980 or thereabouts. Ken, take it away.
Thank you, Dick. Today I wanted to talk a little bit about several issues related to resolution, from the image acquisition point of view till the time that it gets into your camera and you're able to use it. Now, I'm going to go down some avenues that very few other pixels have gone through, and or at least a lot of pixels have gone through this direction, but you may be a little bit concerned about the loss of resolution and how you could actually even get decent resolution by the time it gets to your computer screen. So here's the overview of the talk. I'm going to start talking about aberrations in the lenses and then diffraction effects of apertures. There's several different types of image acquisition devices. I will also talk about the difference between resolvability and sampling density. And there's also what I call the 70% rule, which is a sort of artifact of our common sampling mechanism. And then I'll cover the relationship between field of view, focal length, and pixel density. Now, I've taken a lot of my diagrams from this book here called Modern Optical Engineering from Warren Smith, and I highly recommend that anyone who's going to be doing any work in this area get a copy of this book. I understand that it's now in a 3rd edition, so it is probably at least another ½ inch thicker than this. Now, our pixels start their journey about 93 million miles away at the sun, whether it's directly through the light that ends up coming and coming into our camera after bouncing off of something, or whether it's indirectly as a result of being stored in some kind of biomass or wind energy or anything like that. And eventually it goes through the atmosphere, does a little bit of dispersion, interacts with matter, and it's transported through space until it enters the aperture of the lens. And we're going to start looking at that light once it starts coming through the lens. Now, light is a strange kind of beast. Sometimes it acts like a particle, sometimes it acts like a wave. It's sometimes hard to pin down, and these two aspects of the dual nature of light are going to enter into how it affects resolution. The wave aspect of light is what we can analyze using wavefront propagation analysis, and particle kinds of nature of light can be analyzed using geometric optics or ray tracing analysis. And the illustration I have on the left is a diffraction pattern made by light as it goes through an aperture. And the rightmost one is more like a ray tracing analysis of rays of light as they pass through a lens. So we're going to be looking at both of these and how they interact in order to create the type of resolution or degrade the resolution. So first I'll talk about the particle nature, the nature that we can analyze with ray tracing. The light comes through the lens through, actually it's compound lenses, several lenses, maybe up to 14, 15 lenses that are connected in different ways in order to counteract some of the types of aberrations that we see. There's a point spread function which is inherently related to resolution, and that says how an infinitesimal point looks when it gets through the entire lens system. The types of aberrations that occur are spherical aberration, coma, astigmatism, chromatic aberrations, as well as distortion, barrel distortion, pincushion distortion. And we'll look at each of these in turn and see how they affect the resolution. So spherical aberration is how focus varies as light goes across the aperture from the center to the edge of the aperture. So as you can see over here, the rays in the center are converging right at this point, whereas the ones that came from the edges are converging at that point. You can try to put your you can try to focus this so that it'll be appropriate for the center rays or the edge rays, but you can't get it in focus for both of them at the same time. And this is usually something that we try to correct really well for in lenses, at least across most of the lens. Maybe at the very edge, that will be the place where it gets extremely blurry. But most of the content that we have will be located towards the center. And so if we lose a little bit of resolution as we go off to the edge, it really doesn't matter all that much. The next kind of aberration is called coma. This one's a little bit more difficult to imagine. But basically, as you move across the aperture, the magnification will change. So maybe in the center, you'll see something that is, say, 1-to-1 in size, and then as you go towards the edge, it'll be more like 2-to-1 in size and magnification. As a result, you'll get a point or at least a round area that will scale anisotropically. It'll scale more in one direction than the other, and you'll end up getting a point turning into a tear shape like this, or a comet. I believe that most of the lens manufacturers try to accommodate this as best as possible, because this is probably one of the most disturbing kinds of distortion that we wouldn't be able to deal with very easily. The next type is probably familiar to those of us who wear glasses, at least the astigmatism part. Astigmatism and field curvature are intimately related. They're almost the same thing. They're both different types of curvature. Field curvature is sort of a general curvature where the focus is not on a plane, but on a curved surface instead. And astigmatism is when the curvature is different in one direction than another. So most cameras are radially symmetric. The lenses are ground to be round, and so you very rarely have the astigmatism. But field curvature is something that you have to deal with, and it may be a little bit difficult to distinguish that from the spherical aberrations. Now, astigmatism and field curvature, we can try to do deconvolution on. I'm not sure whether we can do any kind of undoing of the coma. Spherical aberration, might be able to be reversed using deconvolution, but it's best to try to get rid of them as much as possible in the lens. The next type of aberration is chromatic aberration, and that's where the aberrations or even the scale varies with wavelength. The most common is when the scale varies with wavelength, where the red pixels, for example, will be over out here, and the blue pixels, the blue area, the blue component of the color would be over separated somewhat. Now, those are actually really easy to correct just by using some kind of radial remapping, a nonlinear remapping. And it's especially apparent in lenses that have a much wider field of view, something like a 10 millimeter lens, or especially something that ends up having more barrel distortion, which I guess is one of the next things that I'm going to be talking about. And that is when straight lines don't map to straight lines anymore. Typically, the distortion will be rounded like this. This is the barrel distortion. The pincushion distortion is the opposite. And so we will apply some kind of a nonlinear pincushion distortion correction in order to counteract the barrel distortion. So that's easy enough to correct, but it doesn't really affect resolution. It affects a little bit because you're changing the pixel sampling density at particular places, but it's pretty much infinitesimal. The next section here we're getting into is the wave nature of optics. And many people sort of ignore this, so I started looking into the numbers, plugging numbers in as to the actual dimensions of things that people use. Now, this equation over here on the left is the equation of the intensity of a point distributed through space as it goes through the, this is through the imaging plane as a function of space as it passes through a circular aperture. Now, that J1 there is the Bessel function of order 1, which sort of looks a lot like a sine wave. And so it's really like sine x over x, where this is going to be like the reconstruction of that particular point, which would normally be, the Bessel function would be 0 at this point, but because you're dividing by itself, it ends up having a value of 1. The first null will come over here. Now, these things here are this is much larger than it actually is. These ringing things here are much smaller. So the thing that we're concerned about mostly is this. Now, the interesting thing about that is that as the aperture gets smaller, this hump will get wider, which seems a little counterintuitive. But I believe it's probably a manifestation of the uncertainty principle. As you try to squeeze something a little bit closer in one of its properties, it expands in another. Now, the center part here is called the airy disk, and that's what we're primarily concerned with as far as resolution. Now, the diffraction will limit our resolution, and here are some ways of thinking about resolution due to diffraction. If the pulses are too close, then they sort of merge into one, and you get one hump there. Over here, they're just barely far enough, and you can sort of resolve it, but you can't really see the peaks separately. Over here, they're separated far enough that you can see two individual humps, and here they're even further. This is probably one of the most common mechanisms for determining resolution due to diffraction, and it is related to the wavelength of the light and the F number. So the smaller the F number, the smaller the distance between, the smaller the F number, the smaller the distance over there. The larger the F number, the larger that gets. And for higher wavelengths like blue light, the diffraction, the airy disk gets larger. Let's look at some of the implications for that. So visible light varies between about 400 and 700 nanometers. And at F11, we plug the numbers in, and we get that the airy disk radius would be 9.4 microns. And for blue light, it would be 5.4 microns. But the pixel size for typical digital SLRs is 6 microns, which sort of implies that, at least if you look at the Rayleigh criterion, where you'd like the distance to the first null to be approximately where you'd have your pixels, the blue light would probably be sampled adequately enough, but the red light is severely undersampled. I'm sorry, that's the opposite. So what is it that I'm trying to say here? So at F11, if you're sampling for RGB pixels on a cell phone or something, the pixels are going to be too close. your spot is going to be way wider than the pixel separation. So in fact, you're wasting those pixels. You may as well have pixels that are much further apart. If you have the bigger pixels, then this is probably pretty well matched for the digital SLRs. There are some CMOS imaging devices made by Micron that have 1.75 micron pixels, and at f11 at least, the spot, the airy disk, would be covering 3 to 4 pixels, so you're really wasting those pixels. Now, f11 happens to be a pretty magic number in that it is pretty well matched, at least with the blue light here, so that you can get adequate sampling for that when you're using a digital SLR. If you use f16 to try to get more things into focus, then you're wasting a lot of the pixels, and so anyway, the diffraction, we're pretty much right at the diffraction limit for our resolution. If we have smaller pixels, it's not going to work. Cell phones, I guess, typically use a f number of about 5, 6 or something like that. So you can get higher resolution, but you won't have that much depth of field. OK, now onto image acquisition devices. The quaint old imaging acquisition device of film has been around for some time, and it's still being used. CCD sensors, CMOS sensors. There's also mechanisms of acquiring images by putting the light through a splitter, prisms, or maybe having different layers, or having a Bayer pattern. There's different ways of capturing the different spectral samples of light. You can use 1D arrays or 2D arrays, or, well, and also take a look at what a typical CCD looks like. So film generally has 3 different layers. There's a color-sensitive grain in each layer that's sensitive to different portion of the spectrum. And the grain size and the density of the grains will determine what your resolution is. I couldn't find any pictures for that, but this is your more typical digital sensor, which is in a Bayer sampling pattern. Now, you don't really have RGB pixels. You've got red pixels, you've got green pixels, and you've got blue pixels. And you convert those to RGB by interpolating them. So, for example, if you've got 1,000 pixels per millimeter, then the R and B are really sample at only half that density. As you go across here, you can see the blues are 2 pixels apart, the reds are 2 pixels apart. But what about the greens? You might think, well, they're 2 pixels apart, but not really. If you turn your head 45 degrees, you can see that there's a pattern diagonally where the pixels are the square root of 2 apart. So really, for green, your sampling density for green is 707 green pixels per millimeter. And this is one of the places where my 70% rule comes from. Since green is basically really well tied and well correlated with intensity of an image, then the green actually dominates as far as the highest possible resolution that you get. So that means that you're actually using more pixels to represent an image once you've converted from Bayer to RGB than you really need to. So on the bottom, so an 8 megapixel CCD will have 4 megapixels of green, 2 megapixels each of red and blue. And so the RGB resolution will be somewhere in between 2 megapixels and 4 megapixels. And I claim that it's at the 70% point. And we'll take a look at that a little bit later. A lot of high-end imaging devices will use a prism to split light up into 3 different directions, and will have individual sensors for those 3. This probably gives you the highest quality because you end up having a red and green and blue pixel for a red, green, and blue sample for each pixel. these images were borrowed from the Foveon website, which makes a unique kind of sensor that is actually layered. So like film, the Foveon image sensor has 3 different layers, and the light will go through the different layers of silicon, each one absorbing particular wavelengths of light and letting the rest through. So with the Foveon image sensor, you actually get RGB pixels as opposed to the Bayer pattern where you either get red, green, or blue pixels. So this is a way of getting much higher resolution, especially if you're limited by your optics. You can squeeze out more resolution this way. Now, panoramic cameras use a one-dimensional array that's arranged sort of vertically, and they'll sweep it around 360 degrees, scanning around the scene as it goes. Obviously, it takes a while to go around, so if there are things that are moving, then they're going to get blurred out. If you rotate the camera too fast, for example, if you rotate it so fast that you sample every 90 degrees, you're going to be aliasing. You're going to be missing a lot of information. If you move it around too slow, then you're going to be blurring things. So you need to have a good quality lens, preferably with a large aperture that can capture information, the highest possible resolution information. Now, what does a CCD look like? This is what's called an interline CCD, which is different than your standard CCD. A standard CCD will have a photodiode that takes up a good portion of a cell. And that particular type of CCD is one that's used in still image capture devices like cameras. But the interline is used in more video kinds of capture devices. And the reason why it's designed like this is that you can expose the photodiode over a period of time, and then once its exposure time is up, the pixels get transferred to this shield. Now, if you look at this, only half of the area is actually active, or actually less than half, maybe like 40% or something like that. In a standard CCD, the active portion may take up 80 to, well, maybe 90% of this. But for this particular thing, if this is 9 microns, then the active area here might only be 8 by 4. So we may actually be losing things. There may be some details that fall into this area that we're not capturing. And also, we're losing half the light. So this is what the CCD looks like. From the side, there's this transfer gate that transfers the data into this area for the light shield, and then there's a shift register or something that will transfer it out. Now, with video cameras, they use this mechanism to avoid having shutters that have to repeatedly open and close. And this works pretty well. So there's some ways of trying to recover that light. One of the ways is to use lenslets over the top of the pixel to collect the light so that it comes into this well, because otherwise it's just going to get lost. Now, this will collect more light. It will also keep the light going through the correct filter. Without this lenslet, we could have some light coming in from the side, going through this green and hitting the photodiode. If this weren't here, if we didn't have light shields here, if we had a full photodiode, we could actually get light coming in from the side. So this will collect the light, try to give you the maximum kind of efficiency. And here's the results of using this lenslet. I know these curves look the same, but the scale over here is 0.16, and it's up to 0.43 on the top. So there's almost 3 times as much light being collected just by using that lenslet. And so there's 3 times as much light, even though we're throwing away only half of it due to the pixel shield in the Interline CCD. So this is actually working out a lot better and could probably be used for standard CCDs. Now, I mentioned a little bit of color pollution. The Interline CCD device is rectangular. In one dimension, it's half the width. In the other dimension, it's almost the full width. And so that's where this light pollution would come in. You might have some light coming in here from red and going into the green part of the sensor on the other side. So these sort of things need to be dealt with. They are real factors. We've come across that in some of our work, our recent work. Now, resolution and pixel sampling density are a little bit different. And I want to talk about the difference between them over here and talk about certain ways of determining what the resolution of a particular image is. And then I want to look at the intimate relationship between resolution and focal length, because there is a very intimate relationship. Now, these 2 pictures both have the same number of pixels, but they obviously don't have the same resolution. There's a lot more detail on the right than there is on the left. And the way that I generated this picture was actually going into Photoshop, taking the right image, reducing it down by, I don't know, a factor of 4 or something, and then bringing it back up. One way we can determine the native resolution is to take the Fourier transform. Now, the Fourier transform is sort of, well, it's fourfold. It has fourfold symmetry, pretty much. And so I've just taken the upper right quadrant, but the energy where it's brighter indicates where there's more energy. Where it's darker, there's less energy. And you can see with these two plots, the one on the left has its energy primarily concentrated in the lower left corner, whereas the one on the right has it spread out a little bit more. But you can see that it tends to drop off sort of around here. So there is sort of a radial kind of component to the resolution that might be due to diffraction, it might be due to the sampling pattern, or just the fact that well, that it has to propagate through a lot of materials on the way over. Now, one of the things you might notice here is that there's some lines on the left and to the right, these over here, which are, I believe, are probably a residue from the resampling technique used in Photoshop. So it's leaving some extra data in there. Maybe it's due to quantization or other kinds of sloppiness. But ideally, that should be pretty much all that energy should be completely confined to that one corner. Yes?
I believe those lines are actually the correct lines, because in natural images we have more of vertical and horizontal lines, which gives them high frequency around the x and the y axis of the Fourier transform.
So your comment was that you think that those lines are actually a real part of the image, because we generally have more horizontal and vertical lines. And that, I would agree, would be correct for this image. But this image was reduced in size on the left by 1/4. So the resolution of the horizontal and vertical should have been reduced. But you might have, since we have reduced the number of pixels, those pixels cannot actually represent high frequencies like that. So those had to have been introduced by the resampling process. Yes, Lance?
I think it has to do with the integer scaling, too. And if you look at the original image, there aren't strong vertical and horizontal elements in it.
You're right. There aren't vertical and horizontal elements in the original peacock image here. Maybe the legs. But yeah, so Lance was saying that he believes that it's probably due to the resampling artifacts, too. Well, regardless of those resampling artifacts, we can look at the FFT and see where the energy is concentrated. And this is the original FFT that I took without being cropped. The previous one I had cropped a little bit on the right. But this wasn't cropped, and these are the dimensions that correspond to the full image. And I just by hand said, okay, well, where does the energy drop off? And it tends to drop off right around here or right around there. And I just did that by eyeball, and then I measured how far it was. And it turns out that it's, well, 69%, 64%, which is pretty close to the 70% that I had suggested as being the native resolution of a Bayer sampled image. This image was sampled with a Bayer sampling pattern, then reconstructed. So what this is saying is that you can actually shrink your image by 70% in each dimension, throwing away half of the pixels, and still you won't lose any detail. Hard to believe, but it's true. So that's one way of doing compression, lossless compression. Another way to determine resolution is by resizing an image, and that's what I'd done with the, well, I'd sort of done that a little bit with the peacock image. So the idea here is to take your image, shrink it, expand it, subtract it from the original, and amplify the differences to enhance the contrast. So in Photoshop, I've done that with this peacock image. And granted, there's going to be some amount of maybe noise due to the resampling, or I'm not sure where the differences come. But at 90% reduction, there is some energy still left in there. But the thing to note is that the 90% and 80% really don't look very different at all. They're pretty much identical. So we could shrink the image down to 90%, we could shrink it down to 80%, and we're not losing any information there. If we start looking at the 70% image, you can see the peacock head, it gets a little bit brighter. And then going down to 60% and 50%, there's more of the image gets brighter. So that indicates that residual that's due to the higher frequencies is becoming more apparent at 50%. So this is yet another experiment that proves the 70% rule for Bayer patterns. So I was looking at what resolution means. I had done some work with panoramas over at Apple, and we started out working with cylindrical panoramas. And people could compare their panoramas and say, oh, mine has 3,000 pixels across, yours has 3,500, so yours must be higher resolution. Then at one point, we introduced cubic panoramas. And it wasn't quite all that natural to try to compare them because they're measuring different kinds of things. So when you do have a panorama, how do you compare the resolution? Certainly the number of pixels doesn't really help any. And pixels per inch is pretty much meaningless in a panorama. But pixels per degree is something that ties the image into the 3 space, and that gives us a better idea of what the actual resolution for a panorama should be measured in. And I'll go into how I believe that way. But first, if we look at a cylindrical or spherical panorama, we can take the circumference and divide by 360, and that'll give us the resolution in pixels per degree. For a fisheye that's 180 degrees across, you can take the diameter and divide that by 180. For a cubic panorama, I do have a formula over here, face width times pi divided by 360. And I will get into how that formula was arrived at, but here's a way that you can compare these. Having a panorama that's cylindrical or spherical at 2496 pixels would be equivalent in resolution in terms of pixels per degree for a 1249 pixel fisheye image with 180 degrees, or a 795 pixel cube face. And all of them would be equal to 6.9 pixels per degree. Now you might say, well, there's going to be a higher pixel density in different parts of the image. But what this is actually measuring is the minimum pixel density as determined by the focal length. And so we'll make some definitions over here. That panoramic resolution will be the angular pixel density as determined by the focal length. Now, the focal length means different things for different types of geometry. For a plane, it is the distance to the imaging plane. For a sphere, it is the radius of the sphere. For a cylinder, it's the radius of the cylinder. So, and that would be the distance to the imaging surface at the center of projection. So obviously with a plane you can take the distance off to the side, but that's not the closest one. You want to get the one that is the distance that's perpendicular to the imaging plane. Now I've got a few more details at my website, and I'll just show that to you in just for a moment. You can look at it a little bit more. Here, let's see if I can get the cursor over there. Let's see. Cursor. There it is. Okay, so let me just do this. So we determine a standard for panoramic resolution by defining the focal length as being the distance to the imaging surface of the center of projection, and that the panoramic resolution will be the angular pixel density expressed in units of pixels per degree as determined by the focal length. And so here's some formulas for some of the different kinds of sampling of the 3D space. And there's a few calculators here determining the resolution of a perspective lens, resolution of a fisheye lens, resolution of a given panorama in either cylindrical or equirectangular, spherical, or cubic. There's the field of view of a window at a particular resolution, size of a window you need, the number of pixels that you need for a given angular resolution. So this is a way that you can compare different representations. And one of the things that I was looking at was, what is the break-even point between a cylindrical and a cubic projection? And turns out at about 124.8 degrees, they use exactly the same number of pixels. Once you start exceeding that in a cylindrical panorama, then you're going to be using a lot more pixels than you really need. So anyway, you can take a look at that at your own leisure. Let's see if I can get this. Okay, so what does it mean? What does focal length really mean? It turns out that there is this, as I mentioned before, there's this intimate relationship between the focal length and the panoramic resolution. Well, I didn't mention the panoramic resolution, but with the resolution in pixels per degree. So I'm going to claim that focal length, even though it's given in millimeters, is actually millimeters per radian. And I'll get into the reasons why that is. So if you have a sensor that has a certain number of pixels per millimeter, and your focal length is a certain number of millimeters per radian, and you convert the radians to degree, then your focal length is directly proportional to the number of pixels per degree. You double the focal length, you double the number of pixels, the angular pixel resolution of your image. And the reason why I like this result is that it gives us an idea of how the pixels on the imaging plane relate to rays basically in 3 space. Just by thinking of the focal length as a particular distance to the imaging plane doesn't quite give you that feeling. Now let me show you why the focal length is why it really should be considered to be millimeters per radian. here is a triangle from elementary trigonometry. The tangent is equal to the opposite over the adjacent. So the opposite is h over 2. The adjacent is f. This is the focal length to the imaging height. So that tells us that the tangent of phi over 2 is h over 2f, or if you start getting close to the center when this angle is small, then we can approximate the tangent of the angle by the angle itself. So that means that phi over 2 is h over 2f, or if you work it out, your focal length is approximately equal to the height divided by the angle as the height approaches 0. So that yields directly the fact that the focal length is so many millimeters per radian. Now, radians are actually sort of non-units. They can sort of come and go as they will. They aren't really natural, but this derivation shows that it does actually sort of fall out and tells us the intimate relationship here between the focal length and the pixel density. So, in conclusion, I have taken you on a little bit of a journey showing how your pixels got to where they were by going through the lens, having different types of aberrations in the lens, the diffraction and the wave nature of the light. And then that pixel sampling density is not necessarily the same thing as resolution, even though sometimes we will call them the same thing. Resolvability might be a better word than resolution to distinguish between those two. You probably shouldn't really use more pixels than you actually need for an image. Otherwise, you're wasting the bytes. It may give you some better quality images on some devices, but you can always expand them analytically or computationally to generate more pixels. You don't really have any more detail by having those pixels, so you may as well toss out those additional pixels. The 70% rule sort of fell out of the Bayer sampling notion, and it's been proven, at least experimentally here, that it actually does hold up. And the final thing is that that the focal length is basically the resolution, or at least the pixel sampling density. So if we got any questions, Genevieve?
So focal length is related to pixel density, but higher focal length will often lead to smaller field of view. So you also have to consider this as being a key component when you do acquisition. You would often want to compromise between field of view and higher density.
That's true. The comment was that when you increase the focal length, then you're also decreasing the field of view if your imaging device is the same size. And so yes, if you double the focal length, then you probably need to capture twice as many images in order to capture a full 360-degree panorama. That's right. Any other questions? Steve?
Doesn't your conclusion about the effective resolution of those Bayer reconstructions depend a lot on the Bayer reconstruction algorithm?
That's true. So probably the comment was that the 70% rule, the 70% conclusion that came from the Bayer sampling pattern is a function of the type of reconstruction that you use. So yes, typically 1.4 is probably the best possible case that you can do. I doubt whether you could increase the resolution any more than that. I don't think it's possible due to the Nyquist sampling theorem. And typically, your reconstruction is a lot worse than that. Dick maintains that it's something more like 1.8 instead of 1.4. So you do lose a fair amount. That's right. Any other comments? Corrections, maybe? Yes? Lance?
The examination of the spectrum that you showed, that the reason that it's kind of dimmer in the upper right-hand corner is because it is a square sampling grid, and those frequencies are now sampled at root 2 instead of unit intervals.
Good point. Lance's comment was that the reason that the spectrum didn't show very much energy in the upper right-hand corner was that the diagonal frequencies are actually being sampled at a pixel sampling density of 1.4 pixels instead of 1 pixel, and so they're inherently going to have less resolution in that direction. So make sure you get one of these if you're going to be doing any work in optics. I've really enjoyed it. I'd be interested in seeing what edition 3 looks like of the modern optical engineering book.
Thanks, guys.
Thank you. Thank you.